My name is Ákos Rektoris and I'm a product manager at StuSoft. I would like to talk about new features of FEM design, which are about co-design collaboration via 3D models, or as we call it today, via building information models. FEM design had relationship with designer tools so far, CAD drawing-based coordination or 3D model-based collaboration dedicated to major design tools like Tekla structures or Revit, or visual programming-based modelers like Dynamo and Grasshopper. The latter is due to the API, Application Programming Interface, developed by StuSoft. But what about supporting open source connections, such as IFC, whose mother and so the inventor, developer, and maintainer is Building Smart. IFC has a long history and supported worldwide, but only the Building Smart registered number of IFC supporters is more than 300. IFC has been developed for many purposes, like coordination, energy or structure analysis, facility management, manufacturing, cost estimation, and so on. But for us, structure analyzers, the most relevant IFC subsets are the ones defined for collaboration with different design disciplines, architects or MEP engineers, for the purpose of coordination. Coordination can be done via the old, but still the most supported popular version called IFC 2x3 coordination view, and via two relatively new versions called IFC 4 reference view and design transfer view. There is a brand new open source file format called SAF, Structure Analysis Format, developed by Nemetschek brands and analysis software companies like StuSoft. But what are the major differences between the two formats? They are used in different workflows. IFC is for coordination, model referencing of physical bodies of construction elements created mainly by architects. And SAF is for sharing parametric structure analysis models between structural modelers and analyzers. While the structure of IFC is more complex, so you need a visualizer or a viewer to understand its content, then SAF is an Excel-based, easy-to-understand format. And as a side note, you already know that engineers love Excel. FEM Design 20 supports both workflows. Let's see the IFC-based workflow first. Architects send physical models, and FEM Design automatically converts the load-bearing elements to analytical members. Depending on the reference line or reference surface position of the IFC element, FEM Design sets the axis or plane of the analytical members. We need continuous models for finite element mesh-based analysis and design. To achieve this goal, FEM Design gives new, easy-to-use and fast tools, so-called adjusters. In case of SAF, they receive analytical model defined by structure engineers like draftsmen or analyzers. The model is parametric and continuous, so here we really just have to import and use them. And not just construction elements, but support and connections can be shared via SAF. The only task here is to match the database between the SAF sender and FEM Design, so the cross-section and materials. Now let's see the two workflows in live. First, the IFC workflow with the adjusters, and then the SAF workflow. I switch to a modeler. Now I use Oricad for the demo, and I use this demo file. This is a training material of Graphisoft. And here you see the model in live. So this is the whole project. But in a professional modeler like Oricad, you can easily filter for the elements relevant for structure engineers. So you can filter for building elements only, or construction elements only, or with one click, the core of the load-bearing parts. And this is the input we need for structure analysis. If I have a section view of this project, here you can see that, for example, the slab is a composite slab containing different layers, skins. And if I turn on the filter for load-bearing core parts, with one click, you can see the elements relevant for our design later. Here, I also turn on the stairs. I can use the stairs as reference objects for loads and so on in the receiver application FEM design. Now I just go to Save As, choose IFC file format, choose a proper translator, and then I save this file. Now I save 2x3 version of IFC, but of course I can use IFC 4.2. Now I save it and go to FEM design. Here I just use the open command, set IFC as a file type. Here you see the IFC file and just open it. Click on open. Here I can set the position of the axis and the plane of the analytical members. We can automatically put it in the center of the physical bodies, or we can keep the original reference lines and reference planes of the elements. There are two more options here. After the import, I can display the result of the conversion, how it's correct or not. And the last option is for the reference object. So for example, I would like to import the stairs or other elements together with construction elements. And then I click OK. And there is the mapping table. I can also map the cross-sections, but the program automatically runs the so-called profile recognizer and try to define the best suitable profile for the element. I just modify, I just map the materials, for example, 2 different concrete materials and 1 steel material. Then I press OK. The import is very fast, as you see. There are no errors. And there are 4 warnings. The warnings are about the stairs. Here you see the ID stairs. Because the program is not able to convert them, the program uses them as reference model only. The reference elements and the conversion result is stored on a separate layer. We call it imported solids. And if I turn on shading mode, here you see the colors that everything is green except the stairs. They are blue. Maybe I can use transparency and you see better the stairs and the construction elements. Okay, now I can hide the reference objects if I want, and now I can focus on the analytical members. As I mentioned before, the program automatically converts these elements. What is the issue here? That we use the center position of the elements. That is why the analytical members are not connected correctly. But as I mentioned before, FEM design has new functions to adjust the elements and create a proper continuous analytical model. Let's start with walls first. I show only the walls and hide all others. And here you see, because of solid element operations, for example in ArchiCAD, there are small holes, voids inside elements, and also small parts which are not necessary in analysis. We already have a special command for this, the correct model function, and if I select all walls and clear all functions, just focus on the small parts, I can run a quick check, and as you see, the program removes the openings and the unnecessary small parts if I click apply. Then I exit from the command, and as you see the result, the walls are modified. The unnecessary parts are removed. Now I show you that I use 9 steps to create a continuous model. I done the first step, remove small parts, and now I would like to create so-called stories to use them as an adjustment plans for later model modification correction. Now I show all elements and I show only the slabs, hide all others. And as you see, there are differences in the position of the slabs, especially here. There is a gap or a level difference between the slabs. First of all, I add stories to all slabs with one click. It's very fast, as you see. And then I would like to adjust the slabs to the stories. How I can do that? We have a special command. It's a totally new command in FEM Design 20. Adjust analytical models. And there are commands for offset functions and stretch functions. Now I would like to offset the slabs to the plan of the stories. And with one click, I select all slabs. And here you see the program automatically correct 5 slabs and move them in the position of the story. So if I see a side view, you see everything is in the story plan. Okay, then I show again all elements. I show all. And now I would like to move the beams to the stories as a next step. As you see, the beams are not in the story plan. I can use the same command, adjust or offset beams to stories. Just select all beams with one click. And as you see, the program automatically corrects more than 100 beams and move them in correct position. Now, what about the columns and the walls? As you see, they are over to the stories. So I can now, instead of an offset, I can use so-called fit or stretch or cutback commands. Now I would like to fit the walls to the stories. With one click, I can select all walls. And as you see, it's very fast. The walls are adjusted to the stories. And here you see the columns. I can do the same. Just select the columns, and the program automatically fits the columns to the stories. Okay, now the height position is correct of all elements. Let's see some other issues. Here you see that there is not so good correct connections between walls and slabs. And also walls to walls. And if I turn off transparency, you can also see that there are gaps between the slabs and the walls. I can easily fix them with one click. I can use the so-called adjust shell elements. And if I select all shell elements, with one click, the program connects correctly the walls, the slab. There are no gaps. I think it's very, very fast, this algorithm. I can do the same for bar elements. Just select bars. And with one click, if I select all elements, the elements are connected. If you check the beam and the wall connections, there are gaps between the beams and the walls. And also, if I rotate the model, here you see that there are also gaps at the side of the elements. How I can solve this issue? I can use the fit command, but not to stories or axis. You can also stretch or cut back elements to axis, but you can adjust selected elements. So now the target element is the wall, and now I would like to fit the beams to this element. With one click, I can fit all beams to this wall element. And let's see the last step. Each step is I can correct a slab to beams. It's not important because we can keep these small cantilever parts, but I think it's much better for finite element calculation to fit these elements, the slabs, to the beams. I can use the same command, but in this case, the target elements are the beams. And then I would like to select only 4 slabs. I can do it with multi-selection. just select the 4 slabs, and if I zoom in and press enter, you can see that the program automatically corrects these elements. So you don't need any manual element editing. I think the model is ready. Continuous. Finally, before I run analysis, I can check the correctness of the model. I can use again the correct model, select all elements, and run a quick analysis for all elements. And if clicking auto, it makes some changes. And I think now the model is ready for calculation. I always use finite element mesh generation to check the correctness and continuity of a model. Just click prepare. And if there is no warning error message, that means that the model is 100% correct for analysis. Okay, then we need to put support loads, and we can run analysis or design. Okay, let's see the other workflow, the SAF. I go back to ArchiCAD because there is a new function of ArchiCAD 24. With one click, you can create analytical model or analysis model within the physical bodies, but only in the load-bearing elements. Let's click on this function. As you see, it's very fast, and I can hide the physical body. So here you see the analytical members, bars, and the shell elements. You can also show nodes if the model is continuous. Green shows that the elements are continually connected. You can see the end nodes connections. For example, there are hinge connections at this end of the bars. And you can also create supports in slabs, beams, walls, columns, and so on. What we need, just click save, but before I do that, I show you the mapping. As I mentioned before, it's very important to map the database between ArchiCAD and FEM design. So for cross-sections and materials, just click to SAF translators. And here you can see the ArchiCAD materials used in this project and the profiles. And you need to map them to proper FEM design materials and profiles. It's very easy. You can go to a catalog and you can import the FEM design catalog. And here you see now all materials available in FEM design can be mapped now. And also for cross-sections. So here you see the FEM design cross-sections. Then I just click save and choose Excel format, as I mentioned before, although we call it structure analytical format, but it's an Excel file, and I can save it. Now I open it in Excel first. You can easily understand the content of the file. There are different worksheets, one for project data, another one for model data. Here are the materials mapped, so you can see here the final materials, so the FEM design materials, the cross-sections also here. This is the FEM design profile thanks to the mapping. Here you see the nodes, the beams and the columns, the surface elements like slabs and walls, then the openings, the edge connection means line supports, the surface support, and here you see the hinges I show you for some bars. Then I can close this Excel file and go to FEM design, go to open, choose SAF file format, and here you see the ArchiCAD file. I export it now and I open it. You need to set a design code, and voila, the analytical model is here. It's amazing fast, I think. And what is important, that here the elements are connected continuously. Here you can check the materials and the sizes. Thanks to the mapping, we got the same profiles and sizes, materials. Here you can see the end connections, they are hinges. And here you see the supports. You don't need any further steps because we receive a correct analytical model. But as I mentioned before, now I check it with finite element mesh generation with one click. And let's see the result. There is only one warning, and we can investigate this. If I zoom in, you can see that there is a very, very small gap between the beam and the slab. That is why the software sends us a warning that too small finite element was created. We can keep this for analysis. I don't think it's really cause an issue for calculation, but I can easily correct it if I select all elements for the correct model command I showed you before, and use the merge region lines function. And if I start it, the program show you the problem, and then I can fix it. And if I click apply, as you see, the program remove this small gap between the elements and connect the elements correctly. So if I go back to finite element mesh calculation and just click prepare, now we got a perfect finite element mesh for the whole building. And now what we need extra is to define loads and run analysis and design. So as a short summary, in FEM Design 20, the 3D model-based connections have been supplemented with the support of open source workflows. And I think that's all. Thank you for your attention and enjoy the new FEM Design 20 and its new skills for collaboration with design teams.